All right, welcome to lecture 36. These are the last two. So 36 and 37 are the last two lectures where we're going to cover new content. The two lectures after that are going to be review. So just keep that in mind. Anyway, for today's lecture, the very first thing we have is a quiz. So you can just you can click from the slides, you can click from the course website. But once you get to the quiz, again, a reminder to fill out the Meta EIR survey. You guys are doing pretty well. I tried to get a little punny with my options, so hopefully you guys enjoyed the humor there. But this question is worth 0 points, so it doesn't matter what you select. So I'll let you guys do that on your own time because we do have a lot of cool stuff to cover today. Let me stop my video. All right, so first question, in the residual graph G, we have two vertices, U and V, such that the sum of the capacities, so we have two vertices, U and V, such that the sum of the capacities on the edge from U to V, so we have one edge going from U to V and one edge going back from V to U, is less than the initial capacity of the edge between U and V. Is this possible or impossible? So this is the residual graph, GF. So our original graph, G, had some edge from U to V with some capacity, let's say 10. And what we're asking is we're saying, well, we have a residual graph where the forward edge has, let's say, 4, and the backwards edge has, let's say, 5. So 4 plus 9, they add up to 9. 4 plus 5 adds up to 9. So the question is that possible with our max flow algorithm? Would that happen? Yeah. No. Yeah, it's impossible, right? So because these two capacities, the forward edge and the backwards edge, so the edge going along the same direction as our original edge, plus the edge going in the opposite direction, will always add up to the total capacity, because the forward edge is how much capacity we have left that we have not used up, and the backwards edge is the capacity that we have used that we might want to undo. Does that make sense? So answer here is impossible. Next one, there can be an instance of max flow where some of the outgoing edges from the source S and some of the incoming edges to the sink T are not used to their full capacity. Impossible or possible? I say it possible, yes. We actually saw several examples in class where this was the case, right? So again, the max flow is going to equal to the minimum cut. So the minimum cut does not necessarily have to be the edges coming out of S or going into T. A very simple example you could imagine is, let's say you have something like this. Hey, what's going on? So this is 10, 1, 1, 10. We have an edge here going up by 1, right? So the sum of these two edges is 11, right? The sum of these edges is 11, but the maximum flow is only 1, right? So it is possible for there to be an instance of max flow where that doesn't hold. All right, there exists a vertex V other than the source and the sink where the incoming flow is less than the outgoing flow. So when we have a flow, what this is saying, it is, so what it's saying is that there can be, so we have S, which is our source. So obviously our source, when we have a flow, let's say the flow itself is 3 and 2, right? The amount going into S is always 0. So the amount can be anything, right? The amount going out is going to be our flow. And then for T, the amount coming into S is can be non-zero. But obviously there's nothing going out, right? They're called our source and our sink. So what this is saying is there exists some other vertex, let's call it B, where the amount going in is not equal to the amount going out. Is that possible? Serena says impossible. I say, you think possible. Yeah. Right. So you might be confusing the capacities of the edges with the flow, right? So if we go, so you're right. So let's go back to the example. So the example, okay, I don't know what I did there. Anyway, the example I had before was we had S, we had T, we had an edge here with capacity 10, capacity 1. And then we had this edge with capacity 10 and this edge with capacity 1. And we had this edge going up with capacity 1, right? So you are right. The capacities don't have to add up. But the flow, anytime you have a flow, so the flow is going to be, we push 1 here, 1 here, and 1 here. And you'll notice that the amount going into this node is 1, the amount coming out is 1. The amount going in is 1, the amount coming out is 1. So the definition of max flow is that for every vertex that's not the source in the sink, the amount going in has to equal the amount going out, because we don't create new flow in the middle of the graph. We only create it from the source, and we only make it disappear in the sink. So this is actually impossible. Cool. Suppose we have a graph with integer capacities. Can we always find a single edge and increase its capacity by 1 to make sure the value of the max flow increases by 1? Yeah, Vincent? You are the capacities do have to do with the max flow in the sense that they, like you can't have a flow that's bigger than your minimum cut, right? And your minimum cut is defined by the capacities, right? So you can't push more than a certain. So what this is saying is, let's say I have a graph. So a very simple graph would be this: from S to T, I have one edge that has capacity 10. So my maximum flow is 10, right? Because I can just push 10. Now the question is asking, can I increase that maximum flow? Can I change the graph so that the maximum flow is now 11 by increasing the capacity of just one edge by 1? So in this graph, obviously I can, right? Because I could just say, hey, if the capacity of this wasn't 10, if it was 11, then now the maximum flow is 11 because I can push 11. Now the question is, can I always do that? Yeah, so that's the right answer. Why not? Who can think of? Yeah.
Because if like capacity of like another edge was like 9 or something, it would be the next.
Yes, perfectly. So the simplest example you can think of is probably something like this, where the capacities here, let's say, are both 9, right? So the maximum flow is 9, but I cannot increase it by just increasing one of the edges, right? So the answer here is sometimes. So sometimes you can, sometimes you cannot. Does that make sense to everyone? Yep. Okay. So next question, suppose we have a graph with integer capacities and there's a non-zero max flow between a source and a sink. We want to increase the capacity of some of the edges in order to increase the max flow. Do we need to increase any edges capacity by 2 or more units? So again, it's similar to this question. You're going to have a graph, you're going to have a max flow. So you're already pushing as much as you can through it. Now your task is, I want to increase the flow by one value, by 1 unit. The question is, can I always do that by increasing as many edges as I want just by 1? Or are there cases where I may have to increase some edge by more than 1?
Multiple edges go to the same vertices to be increased by 2. We have 2 more going into.
Okay. So one suggestion, if I'm understanding correctly, you're saying I have some vertex that has multiple edges coming in and only one edge going out. And you're saying, hey, in order to increase my max flow, I will have to increase the flow here by 1 and the flow here by 1, which forces me to increase the flow here by 2. Okay. Everything you've said is correct. Do you have to increase these 2 edges by 1? Yeah. You don't, yeah, could you explain why? So yes. So another way, that's exactly right. So your logic is perfectly right. The assumption that you're making that there's going to be 2 edges that you're going to increase by 1, both going into the same vertex, this is not true. Because if you have some graph from S to T, right? If you want to increase the max flow by 1, by our algorithm, all we need to do is we need to find a path from S to T that has whose minimum edge is 1, right? So if there does not exist a path, I can just, in the worst case, I can create a new path consisting of a bunch of edges that have capacity 1. And that path will let me increase the flow by 1, right? So it is always possible to do it by just increasing edge capacities by 1. Okay. All right, next question. The company, so let me clear this. Algorithm is preparing to transition back to office. They have N offices and M employees, and they need to assign to these offices. Given COVID restrictions, each office has a capacity for how many employees can be in that office. Each employee also has a list of preferences for the offices they want to go to. Okay. We want to assign as many employees to offices as possible, as long as every employee is assigned to a single office. So they can only be assigned to one office. They cannot be assigned to multiple offices. And the office they get assigned to is within their driving distance. And the number of employees assigned to every office is less than or equal to the office's capacity. Can you do this with max flow? I hear a yes. Leander, do you want to describe what the graph you would construct would look like?
For the people, I'm going to source nodes to the people that's on the left side. It'll be how many places they're going to drive to. And on the right side would be offices, how many people they go.
Okay. So if I'm understanding correctly, and definitely correct me, you're going to create a graph where every employee becomes a node and every office becomes a node. You're going to have a source and a sink. Can you guys see that? Oh, you can. Great. And you're saying that these edges, what do you set? What's the capacity for these edges? The number of places they're willing to drive through. Okay. What's the capacity for these places, for these edges? Right. I agree with this one. So these capacities will be CJ, whereas how many people can fit in that office at most. Now, obviously, this graph has a max flow of 0 as currently defined. So I assume there's going to be some edges going in between. How would those edges be defined?
The edges for the people might just be 1, and in between will be the places they go.
Got it. So you would say there's an edge. So if employee 1 prefers office 2 and 4, you would make an edge from 1 to 2 and 1 to 4. Yes, with capacity 1. Okay, I agree with that. That seems reasonable. Now, I disagree with your capacities for the source to employees. Does somebody else have a suggestion for what that might look like? Yes, Serena? We are actually not taking into account how far the office is. So they have a list of offices they're okay with, right? It does not matter to them that one is further than the other. It's just these are the ones I'm okay attending. Yeah.
regardless of how many offices they're okay with attending?
That's what Leander suggested. That's not quite right. So the number of offices that they're okay with attending is actually already encoded by the edges here. But there's another restriction that we need to make sure we uphold in the problem statement. Yeah, Jonathan?
Would it be that they're only assigned to one?
They're only assigned to one office. So how can we guarantee that each employee only gets assigned to one office?
Can you do the deferred acceptance one for that?
This algorithm, you could use deferred acceptance because the offices don't have a preference. Yes, but that is different from max flow. I'm trying to use max flow for this. This problem is actually easier than what you would need for deferred acceptance, because deferred acceptance you need it when both sides have preferences, right? In this case, only one side has a preference, so we can actually solve it with max flow. But we want to encode that only one employee can be assigned to one office. How do we enforce that restriction with the capacities? Something. Okay, I'm not sure. I'm probably not understanding correctly. Serena, do you have a suggestion? Yes, that's exactly it. So the idea is that the weights from the source to the employee, this edge will be 1. Because what that means is that the amount going out of the employee will at most be the amount going in, which is at most 1. So every employee, even though he has many possible edges, can only pick one edge to take. So that is the one office he gets assigned to. And as Leander mentioned, these edges here are the capacity of the offices. So they will never be assigned more than the number of employees that each office can take. Okay, so that actually goes to the next questions. For each employee I, we'll add an edge from S to I. This should be 1. The capacity has to be 1. The next question actually asks about the capacities for these edges in between. Leander suggested setting them to 1. That works. Do you guys think the answer here is 1 as well? Yeah. It actually does not matter as long as it is not 0. So as long as the edge exists and it is bigger than or equal to 1, these capacities for these edges will not matter because the restrictions are being enforced here and here. And then we're enforcing, the preferences by having the edge exist, but the actual capacity does not matter. So you can actually have this be any of the above as long as it's not 0. Okay. And then office from J to T, we already talked about this, and this is going to be the office capacity. All right, so last question. Suppose there are 2 states who want to run a joint doctor-hospital matching program. The first state has N hospitals and N doctors. Second state has M hospitals and M doctors. So this is like California and New York are running their hospital doctor matching program. Could there be a stable, and every doctor prefers in-state hospitals to all of the out-of-state hospitals, and every hospital prefers in-state doctors to out-of-state doctors, okay? Is there a stable matching where a hospital and a doctor from different states are matched? This is testing if you guys remember the definition of stable matching and also if you're understanding the problem statement. Also 50-50 if you just guess, but Leander, yeah. Okay, Leander thinks no. Do you want to explain or yeah?
It says that all the in-state doctors or in-state hospitals, right?
Yeah.
Basically, it would have, even if they're connected to the out-of-state, it would have to be very high, I guess, priority.
Yeah, very high preference. Yeah. So you have the right idea. That's exactly right. So like the question states, every in-state doctor prefers in-state hospitals, and every in-state hospital prefers in-state doctors. So if you had a matching where you had a doctor from California who gets matched to a hospital from whatever, New York, right? That California doctor prefers some in-state hospital, right? And that in-state hospital prefers him over whatever out-of-state doctor they were assigned to. So that is not stable. So the answer here is no. Okay. So anyway, hopefully you guys can submit that. And yeah, I'll let you guys submit it. And let's get started with our actual lecture. All right, so final exam is on Wednesday. Just again, another reminder, Wednesday, May 11th, okay? Don't forget about it. It's gonna be online. You need to be online at this time. I'll send out more details. Okay. Here's the current progress on the Meta EIR survey. So 72%, pretty good. You guys need like 15 more people, I think, to get to 90. This is from Sunday night, it's at 20%. So, you know, talk amongst yourselves and please fill out the Blackboard course feedback. I think our target for this one was 80%. So each of these are one bonus point for each of these. Homework 10 is out. It is due on Friday. The walkthrough is also out. It's all written. It's a much shorter homework assignment than usual, but yeah. All right, any other announcements from the class? No? Great. All right, so today we're actually going to start covering some pretty advanced topics. And in particular, we're going to cover linear programming and random projections. So, well, first of all, I'm going to do a brief overview of what has happened this whole semester, right? So we're going to do a tour of Comp 285 and everything that you guys have learned over the last several weeks. We are going to have official review lectures on Monday and Wednesday of next week, okay? Then we're going to cover what's next. So I'm going to give you guys a sneak peek at some more advanced algorithms, some more interesting techniques. And yeah, so let's get started. So all of these words on this slide should mean something to you guys. This is all that you have learned from the very beginning when we were doing big O notation and worst case analysis, all the way to stable matchings, which we talked about last lecture. So if I tell you SCCs, you should have an idea of what that is. All of this should make sense to you guys. Is there anything on this slide that you guys are like, I don't know what that is, and I don't remember what it is? Because you guys should, like, you know, pat yourselves on the back. You guys learned a lot of stuff, okay? A lot of different things, all the way from, you know, like we were sorting. You guys remember those days of sorting? We did, you know, knapsack problems, dynamic programming, MSTs, minimal spanning trees. All right, so this is, we covered a lot, a ton of stuff. Darius says that knapsack kind of doesn't make sense to him. So I'll make note of that and try to cover it during the review lectures. This was a dynamic programming problem where we're trying to fit stuff into a backpack. You guys remember? Cool. So that's been pretty fun. I had a lot of fun. It was 36 lectures in total. Those are going to be the ones that we're going to focus the most on the final, just FYI. And I'm going to try to summarize them in the next 12 slides. So if you never came to class, these are the 12 most important slides, I guess, but they're not going to go into a lot of detail. So the general approach to algorithm design, you guys should now be, you should consider yourselves algorithm designers. So when I give you a problem, a computational problem, you should tell people that you are an expert algorithm designer. And the first thing you should always ask yourself about a particular algorithm is, can I do better? Okay, that's a very common question that we ask throughout the class. And to answer this question, we talked about needing both rigor. So we need to be careful about how we analyze the correctness for algorithms, but we also need intuition, right? A lot of times to come up with an algorithm, you need to think at a high level, how would I do it, right? And you start there. So the very first thing we did is we needed more details, because knowing, like, asking the question, does it work and is it fast? This is a very vague question, right? This does not have a very precise meaning if you just ask it. So we spent the first few lectures trying to define what it means for something to work and what it means for it to be fast. And in particular, we talked about worst case analysis. So when we ask the question, is the algorithm fast? We're always considering how long does it take in the worst possible case, right? So the input that you're given, you should always consider when somebody asks you if this is fast for algorithm design, is the worst possible input. Okay. Now, another trouble we ran into when talking about how fast something is that counting each individual operation is very tedious and takes a long time. So we decided to introduce this idea of big O notation, right? And the main idea was that for computer problems, generally we want to run them on very large inputs. So we really don't care about exactly how many steps it's going to take, but we care about how the algorithm changes with the size of the input, right? That's what big O does for us. So this is the formal definition of big O, but the intuitive definition is, hey, I don't care if this takes 10 steps or 15 steps. I just care that it grows linearly with my input. I care that it grows quadratically with my input. I care that it's exponential, right? All right, so the first design paradigm we were introduced to, if you guys remember this, was called divide and conquer. So this is a design paradigm. It is not a single algorithm, it's just a technique for approaching different problems. But we did cover several algorithms like merge sort, Karatsuba's algorithm for multiplication. This was lecture 1. The select algorithm, so quick select. And then we analyzed these algorithms. One approach was to be really careful about how we looked at the pseudocode, we tried to keep track of how things were being split, and then we tried to count how much work we're doing at each level of the tree. The other useful shortcut that we also learned was called the master method. So if you ever have a divide and conquer algorithm, if you can come up with the recurrence relation for it, most of the time the master method can immediately give you the big O running time, right? So this was like lectures 1 through 6, basically. Cool. While we were on the topic of sorting, we also talked about random algorithms. So we actually introduced quicksort, which was an algorithm that randomly picks a pivot, splits the array into those 2 partitions, and then quicksorts each of them. So it's both divide and conquer, it's recursive, and it uses randomness. We talked about how even in the random case, we still want to consider the worst case possible input, and that the randomness is going to be chosen after the input is chosen. Now, for the algorithms we covered in class, your homework assignment introduced you to these concepts. It was Las Vegas and Monte Carlo. For all the algorithms we've covered in class, they have all been Las Vegas algorithms, which means that they are always correct, but the running time might change depending on how lucky you get with your random choices, right? Who remembers what Monte Carlo is? Yes, it is guaranteed to have a fixed running time, but it could be wrong sometimes. Okay, so it's the other side of the coin. Now, one thing that I really want you guys to remember about sorting, and this was the only, like if you guys remember, we always ask ourselves, can we do better? And I will oftentimes point you guys to research papers and be like, this is the latest state of the art or whatever. But we don't know that this is the best possible. So next lecture, we're actually going to talk a lot about what it means to consider, like, what is the best possible way to solve something. But for one set of problems, we do know that sorting, you can do better in some cases. And in other cases, you cannot beat n log n. Do you guys remember the difference between these? In which cases can I do better than n log n? And in which cases have we proven? So mathematically, we have proven it is impossible to do better than n log n. Serena? Yeah. Yes, we didn't go into detail about the proof, but it is helpful for you guys to know that if you're ever doing comparisons-based sorting and somebody claims to do it faster than n log n, they're wrong. Okay, just they're selling you snake oil or whatever, right? They're just wrong. They're lying to you. However, if we know something about the inputs, we can do faster. For example, radix sort can take O of n time if you have inputs that are not too big and they're all integers, because we use bucket sort to sort them, right? So if you know more information about your data, you might be able to design an algorithm that is faster. But if the only thing you can do is compare 2 things, there is nothing faster than n log n. Cool. All right, so beyond sorting and linked lists, we didn't cover beyond sorted arrays mostly. We talked about binary search trees, which are a useful data structure, especially the ones that balance themselves. Do you guys remember there was one binary search tree we talked about that is self-balancing, That's a special name. Red black tree, exactly. You guys don't need to know how to balance the red black tree or what exactly the properties are that it maintains, but you do need to know that if you have a balanced binary search tree, what is the running time of finding an element or inserting an element? Yes, log n, because it is always the height of the tree. And if the tree is balanced, the height is going to be log n. Okay. Then we talked about hash tables. So this was the idea of taking a really, really big universe and trying to hash it into a small number of buckets. If you guys remember, we covered 2 lectures on universal hash functions. And we talked about how in order for this to work, what you do is you choose the hash function randomly from a set of possible hash functions so that your adversary, the person giving you the inputs, cannot give you really bad inputs. That's how we get expected running time of O of 1. And then we also talked about how you don't want to consider all possible functions. This is too many. So you have what are called universal hash families, which are an infinite set of functions that are small. I don't know if you guys have taken some math courses, that should hopefully make sense to you, but you can have infinities that are smaller than other infinities. Okay. We covered that. And then we jumped into graphs. So we covered BFS, DFS, and some applications of it. We covered strongly connected components, topological sorting. Who wants to tell me something about any of these things? Running times, what they're used for. What do you guys remember about any of these things? Yeah, go ahead. Exactly, that's perfect. Yeah, so if you want to do topological sorting, which means you want to figure out in which order you should process things so that the dependencies come first, DFS is great for that because it gives you start and finish times, and then you can sort based on those. BFS is great for the shortest path between your source node and every other node if your graph is unweighted. So if each edge is cost 1. That's perfect. And leads us right to the next subject. We then ask the question, a fundamental problem in graph problems is trying to find the shortest path. We cover a lot of algorithms that are very useful for transit planning, packet routing. These are some really useful algorithms. They're literally like these algorithms are running on your laptop every day when you go visit a website. On servers, they're running every day, right? Google Maps, when it tries to find where to route you, they're using these algorithms, right? We covered Dijkstra, Bellman-Ford, Floyd-Warshall. Who can tell me the difference between these 3? When would you use which one? Yeah.
Dijkstra can't handle negative edge weights.
Great.
So with Bellman-Ford,
Okay, yeah, that's perfect. So yeah, the big thing to remember with Dijkstra is it only works with positive edge weights. Okay. Bellman-Ford handles negative edge weights. What's the cost? What do we pay? So it's like we get to solve more problems, but why wouldn't we just always use Bellman-Ford if it handles negative edge weights as well as positive ones? Yeah, Leander? Yes, Bellman-Ford is slower than Dijkstra. Again, depending on how you implement it, but generally it is slower than Dijkstra. Okay. Now, Floyd-Warshall, so both of these two, Dijkstra and Bellman-Ford, are called single source shortest paths. So from a single node, what is the shortest path to every other node in the graph? Okay. Floyd-Warshall was solving the problem of, hey, sometimes I want to know what is the shortest path between all of the nodes. So not just from S to every node, but between all pairs of nodes, what's the shortest path? So Floyd-Warshall solves it. And something to consider is that Bellman-Ford and Floyd-Warshall were actually examples of something that we call dynamic programming. So this was probably the hardest part of the hardest section, I think, in the course. But we saw many examples, such as longest common subsequence and knapsack problems. Who wants to remind me what the knapsack problem is? Yeah, David?
You have a backpack and you want to fit like as much stuff as valuable as you can in the backpack.
Yes, that's exactly it. So David, like you said, you have a backpack where you want to fit as much valuable stuff as you can. So what that means is that your backpack has a capacity. right? Otherwise, the problem would be easy, just take everything, right? So it has to have a capacity. Most valuable stuff, that means your items have to have some value associated with them. But in order to make it harder, they also need to have a weight that is not exactly the same as the value, right? Because otherwise, if they only had a value and they all weigh the same, just take the things that are the most valuable, right? So this problem is hard, but we solved it with dynamic programming. So again, dynamic programming is a design paradigm where we had a few steps. Step one was to identify the optimal substructure. How do you break your problem down into smaller problems? Step two is once you have answers to the smaller problems, how do you use those answers to create an answer for the bigger problem? And once you have that, then steps 3 to 5 was, okay, code that up, okay? So these two steps are usually the hardest for coming up with a new algorithm. But as you guys noticed in your homework 6 and 7, these are not that easy either, because there's a lot of details that you have to make sure get written down, okay? Yeah. Then we jumped into what we call greedy algorithms, which is sometimes our optimal substructure is so good that we don't actually have to solve all the subproblems. We can immediately make decisions and say, this is the only subproblem we need to solve. So we make a series of choices and we commit. Okay, and this is the last set of algorithms we covered. Proving that the algorithm is correct is usually pretty hard. Generally, you want to use induction. And here's a few examples that you guys should know. Activity selection. So this is given a set of activities with start and end times. I want to do as many of them as possible without conflicting any of the activities. Who remembers the general gist of how this algorithm worked? Yeah, Leander. Yeah. Sort by end time, and then pick the activities in order of the earliest finish time, the earliest end time, that does not conflict with something you've already picked. Okay. Now, if you guys remember why that works, that's great. But it's not that easy, because you might consider, hey, what if I sort by start time? Does not work. What if I sort by the size of the activity? Does not work. Okay. It has to be by the ending time. We talked about job scheduling. We talked about, well, we barely covered this, so don't worry about it. It's not going to be on the final. Huffman coding. And the very last thing we covered was minimum spanning trees. Minimum spanning trees are so important because they bring greedy and they bring graphs together that we actually covered 2 different algorithms to do minimal spanning trees. Who remembers what the algorithms are called? Yeah, Jonathan? Yes, prims and crusticles. So both algorithms are correct because they rely on the fact that for any cut, the cheapest edge will be in a minimal spanning tree, but they work very differently. Prim's algorithm starts at a node and then tries to grow the tree. So you guys should be familiar with running this algorithm. It may be a question on your final. Similarly, Kruskal's algorithm starts with the cheapest edge that does not create a cycle and then keeps adding cheap edges. Okay. All right, the last thing we covered was cuts and flows. So we talked about the minimum ST cut, which turns out is the same as the maximum ST cut. And we talk about the Ford-Fulkerson algorithm, which is used to find the maximum flow. Okay. This is very useful for routing, but it's also very useful for assignment problems, like the one we just covered in the quiz, which is, hey, I've got employees and I need to send them to an office, and I have certain constraints on how many employees can work at an office, and each employee has certain preferences, right? We also talked about the history of it. And then finally, we jumped into stable matchings, which was what we covered last lecture. So I'll just not go too much into here. And now we're here today. So hopefully you guys feel like you've learned a lot. What do you guys think? Maybe, not maybe, sort of. Again, you don't need to be an expert in all of these things. A lot of this stuff, I had to refresh myself as to what it was before I taught it to you. Some of this stuff you don't use that often. Some of this stuff comes up very often. Okay. But the general idea is you guys should feel comfortable having at least a toolbox to try to solve algorithmic problems. So you should try, if somebody asks you to solve a problem, either in an interview or in your job, you have an idea of, hey, is this a graph problem? If it's a graph problem, could I use BFS, DFS, Dijkstra, right? Is this a problem where sorting will help? Is this a problem where maybe dynamic programming will help, right? So you have a lot of frameworks to try to think about how to solve different problems. And that's what we filled in. That's what we like to call the toolbox. Because again, for this class, it is important that you guys know these algorithms, but I will say that this is a very, very small subset of all the possible algorithms that exist out there. Yeah, there's a lot more. There's a lot more stuff. We didn't cover everything, but at least you guys hopefully feel more comfortable trying to solve some of these problems. So a lot of you will probably be taking several of these classes. I actually looked through some of the syllabi for these classes, and they will be covering some very interesting algorithms that will build up on what you guys have learned here, and will give you more practice for it. Especially this one, artificial intelligence and machine learning. I hope you guys take that one. If I get an opportunity, I will try to come back and teach that course, because Meta has a special, they have a program there where they're trying to get it started. But all of these use algorithms that we've covered, and they go into a lot more complicated algorithms as well. So get excited. Who's taking some of this courses in the future? All of you? I will do my best, but I am one person. But yeah.
You teach 365 next semester?
No. We don't have that set up yet, but we are trying to figure that out, because Meta does have, there's a very, not only is it hard to get people from different backgrounds into tech, it's even harder to find people to get into like AI and machine learning. Yeah, so question?
About they'll make things like
350. Oh, operating systems. I don't know that I would enjoy teaching that, but we might. Yeah, I'm sure I can float it around and ask to see if Meta. But I don't. I like algorithms. I like AI operating systems. I did the class when I took it. I did well in the class, but it was not my favorite. I'll say that it's a little too much coding for my project. Anyway. But yeah, so today let's actually jump into, like, let me give you a little bit of taste as to what you might see in some more advanced algorithm courses. These are not going to be very detailed. These are probably not going to be on the final. I'm not going to ask anything about this, but just FYI. One very general problem that we did not get the time to cover in a lot of detail is called linear programming. Has anybody heard of this? Because it's also an applied math thing, a little bit, maybe not quite yet. Okay, so linear programming is the following. It's the idea that you want to maximize some function of several variables subject to some constraints. So this is a very general problem, okay? You can make a lot of problems be this problem, where you're trying to maximize or minimize something, and this is saying, I want to maximize the value of x plus y subject to the fact that x is greater than 0, y is greater than 0, for x plus y is less than or equal to 2, right? So maybe this is like, the cost of buying, some amount of X is $4, and the cost of buying some amount of Y is $1, and I cannot spend more than $2 buying these particular things. And then you can imagine there's a lot of real world limitations that you can rewrite as constraints, inequalities in math, and you're trying to maximize profit, you're trying to maximize goodness in the world. I don't know. So if you can write it mathematically, this problem works. So it turns out to be very general. And we actually, I'm skipping a lot. We actually already saw a version of this problem. So we talked about how maximum flow can be used to solve a lot of other problems in the real world. It turns out that maximum flow can also be represented as a linear program. So if you have an algorithm to solve linear programs, that is also an algorithm to solve maximum flow. Because the idea is maximize the sum of the flows. So for each edge, you define a variable that tells you how much flow is going over that edge. And then you want to maximize the sum of the flows subject to these constraints. None of the flows are bigger than the edge capacities. So that's, x is less than or equal to 10 for every edge, right, or whatever. And at every vertex, the stuff going in is equal to stuff going out. So again, those are inequalities or equalities. So this is actually an example of this. Okay, I'm not going to go into detail exactly how to do it, but just so you guys know. They also have a really nice geometric intuition. So if you guys have never seen this, there's a geometric like way to think about this, which is you can plot x greater than or equal to 0 on your graph. Y greater than or equal to 0 means you are now considering this intersection, right? And you can plot the rest of the inequalities where it turns out that the only thing you're considering is this inner block. So this is the space of solutions. So geometrically speaking, this is the space of solutions that solves, that satisfy your inequalities. And then what you're trying to do is you're trying to maximize x plus y. So if you rewrite x plus y, you'll notice that x plus y equal to some constant is just a bunch of lines with slope -1. So what you're trying to do is you're trying to find the line that maximizes this value. So the constant c, subject to the fact that it has to be inside this shape. It turns out that if you realize this, you'll notice that the solution has to be at a vertex. So the algorithm that does this, and we have a polynomial time algorithm that solves these problems. So any problem that is linear programming, you can solve in polynomial time. I'm not going to tell you what it is. Basically, what it does is it jumps from vertex to vertex, and it tries each of them to see what the values are. Okay. So I only got a few more minutes, and I want to teach you guys more stuff. But basically, that's what I just drew on the board. In general, that was the constraint for 2 variables. In general, you can have n variables, which means you define a n-degree polynomial, like they're called polytopes in some n-dimensional space. And then the way the algorithm works is it jumps from vertex to vertex to see what the maximum value is. Okay. I'm going to skip this part. This is more advanced, but if you guys are familiar with duality, in mathematics, there is something to be said for this program being dual, which has something to do with the fact that the maximal flow is equal to the minimum cut. So that's actually a more general statement. Every linear program that you maximize subject to some constraints has an equivalent linear program that is minimizing something subject to other constraints. And the values of the max and min are equal. That is a more general mathematical fact. Okay, so I'm going to skip this for a little bit because I want to talk to you guys about the last thing. There's something. I don't have time to cover it. We only have 1 minute. Okay, well, it's not going to be on the exam, but there are other algorithms as well that actually come up very often that are really, really cool, that rely on the fact. So just FYI, this is pretty advanced, but if you ever run into a problem that is really difficult to solve, okay, one trick that has become very popular, and this is especially true in the machine learning and AI community, and like in any other community, is to take your data, which is very high dimensional, so it means it has a lot of features, and you project it into a random subspace. And it turns out, so for example, before we leave today, this is really valuable if you guys know this, but I'm not going to go into detail about it. But consider you have a bunch of points in like 100-dimensional space, and you're trying to calculate the distance between all the points. Okay, calculating the distance between 2 points is going to take you proportional to the number of items in each vector. Right, so these are vectors in a 100-dimensional space. So it's going to take you about 100 squared operations to calculate the distance. But something that's very common in machine learning is trying to say, given this point, give me the closest point to it. If you do it in the high-dimensional space, it's going to be too slow. But what we do instead is we find a 2-dimensional plane, so a 2D plane. We pick it at random, so completely randomly. And then we project all of those 100-dimensional points into 2-dimensional points in that 2D plane. Now, how you do the projections has to do with dot products and cosine stuff. It's actually not hard. If you guys have done trigonometry before, this might sound a little bit familiar. But it turns out that if you have a point here, and you map it to lower dimensional space, the points that are close to it will also be the points that are close to it in the higher dimensional space. So you can go from a problem that takes you 100 square operations to find the distance to a problem that takes you 2 squared operations to find the distance. Okay. Now, it's not always right, but it turns out that sometimes just picking random stuff works. So that is like a new paradigm in algorithms. So think about that. And that's it for today's lecture. I'll see you guys on Friday. We're going to cover P versus NP, which is like my favorite topic. So please, if you can make it, please come. I'm really excited about it, but I'll also just record it. So see you guys. All right, see you folks on Zoom. Thanks for coming.